Hello everyone. Here in this video we are going to talk about a very interesting chapter, that is the analysis of LTI system using Z transform. Okay, so we all know what is the full form of LTI. LTI stands for linear time invariant system, right? That is, this system has both linearity as well as time invariant property. Linearity property in the sense means if the inputs are added and given to the system, the output will also change according to the input. That is, if the input increases, the output also increases proportionally. Like that, if the input decreases, the output also decreases proportionally. That is what is called as linearity. And time invariant in the sense means if the input is being shifted in time by this much number of seconds, the output will be response to that same shift. That is, if the input changes in time, the output also will correspondingly change in time. Okay, that is the meaning of time invariance. So a system which satisfies both the linearity as well as time invariant is what you call as a linear time invariant system, also called as an LTI system. So what is the main features or attraction of this LTI system is that every LTI system, as you have learned before, is uniquely identified or characterized by a unique function when we call that as h of n, right? And h of n, and this h of n is what you call as the impulse response of the system. So you see, if this is a circuit, if this is an system, then every system has an input for us to process, and after processing we get the output called as y of n, right? So this x of n is what you call as the input, or also called as the excitation. Okay, and this y of n is what you call as the output, or also called as the response. So you see, just look at the name. Y of n is called as the response. H of n is what you call as the impulse response. So which means that we can from here itself we can understand that this h of n is actually the response of the system when x of n is an impulse signal, right? Or in other words, you will get y of n is equal to h of n. You will get y of n is equal to h of n when x of n is an impulse signal. This is what is the meaning of impulse response. That is, response of the system or output of the system when the input is an impulse signal. Okay, so how do you connect these three symbols? So what is the equation of output? So how do we find the output from the impulse response? We have studied that earlier. That is, y of n is equal to x of n convolution with h of n. This is the equation of finding the output of the system, right? That means once if you know the input and once when you know the impulse response, then looking from these two symbols, by convolving them together, we can get the output of the system y of n. Okay, and just like in Laplace transform, same thing like Laplace transform, one of the main advantage of this Z transform, of using Z transform, is that if I'm applying Z transform to this equation, then I am getting the equation as y of z is equal to x of z into h of z. This is the convolution property that you have studied earlier. Y of z is equal to x of z into h of z. That is basically convolution in time domain is nothing but the multiplication in z domain. Or in other words, just to generalize in all the transforms that you have studied so far, convolution in time domain is multiplication in frequency domain. Here our frequency domain is Z transform. You see, so this is what is the main advantage of using an Z transform or any frequency transform equations, because basically we are converting this convolution operation. This is a very tedious operation. It's a very difficult operation. The equation you're using is sigma n is equal to minus infinity plus infinity x of k h of n minus k. That is the equation for this convolution equation. But here we don't have to apply any of that. Simply find the z transform of x of n, z transform of h of n, and then multiply these two and you'll get y of z. Then you need to find the inverse of y of z to get the value of y of n. That is how we basically solve the given questions, simply doing this same procedure, right? So another advantage of this equation, so from here we can see one more thing you need to know. Here I can tell that the value of h of z is nothing but y of z by x of z, right? Y of z by x of z. I already told you that the meaning of impulse response is because the output will be getting the impulse response when the input is an impulse signal, right? Because the reason is, if the input is an impulse signal, then your x of z is equal to z transform of x of n, right? And if this x of n is a del of n, if x of n is an impulse signal, then z transform of del of n, you will get it as 1. So which means that if I substitute x of z is equal to 1 over here, I will get h of z is equal to y of z. You see, so which is nothing but this equation I'm getting over here. H of z is equal to y of z in z transform, or in other words, y of n is equal to h of n. You see, so this is how we connect all these properties, right? So this is what we call as, so we call this h of z as the equation of, or the ratio of y of z by x of z, and this is called as the transfer function. So what is the transfer function? The transfer function is nothing but the z transform of impulse response. H of z is equal to z transform of h of n, right? So this h of z is what you call as the transfer function, and this h of n, small letter h of n, is what you call as the impulse response. So this is how we apply all these equations together. Okay, now another advantage of checking, another advantage of finding the transfer function using z transform is that we can check whether the system is, this LTI system is stable or not. Or in other words, we can check if this, we can check the stability of the LTI system. We can check the stability of this LTI system looking at the h of z, right? And also we can also check whether this LTI system is causal or not. We can check whether we can check the stability of the LTI system, and we can check the causality of the stability system by simply looking at the ROC of h of z. This is the main advantage of using an z transform, or finding the transfer function in z transform, right? That is, by looking at the region of convergence in an LTI system, we can check whether the system is either stable or unstable, and we can also check whether the system is causal or non-causal, right? So we all know what is the meaning of stability. We all know what is the meaning of stable and unstable system, right? What is the meaning of stable system? Stable system means that if we add all the values of that signal, if you add all the values of the impulse response, that value should not be infinity, or we should get a positive finite value. We should get a finite value. Or in other words, for a system to be stable, we know that if we add all the values, right? If we add all the values of the magnitude of the impulse response, we should get a finite value. That means the value must always be less than infinity. If this condition is satisfied, then the system is stable system. Then the system is what we call as a stable system. Right? So this is how we check whether the system is stable or not, using impulse response. Now, how will I find the system is stable or not? Looking at the ROC of h of z. How do I find whether the system is stable or not? This is in time domain. I can check by simply adding this, right? Adding all the values and taking the magnitude of it. It should be less than infinity. But how do I check the stability of the system? By simply looking at the ROC. Instead of finding the h of n, how do I find the stability of this system looking at the ROC of h of z? How means it's very simple. That is, we all know the equation for h of z, right? H of z, the equation for h of z is that sigma n is equal to minus infinity to plus infinity h of n into z raised to minus n. This is the z transform equation, right? Okay, z transform equation. Assume, okay, let me use a unilateral. Since it's a causal system, let me assume it is a unilateral. Okay, 0 to infinity h of n z raised to minus n. Okay, so now if I want to if I take the magnitude of this z transform equation, the magnitude of z transform, okay, taking the magnitude of the above equation, so magnitude of h of z is equal to sigma n is equal to 0 to infinity magnitude of h of n into z raised to minus n, right? Magnitude of h of z is equal to sigma n is equal to 0 to infinity magnitude of h of n z raised to minus n. This is nothing but less than or equal to, this is actually less than or equal to sigma n is equal to 0 to infinity magnitude of h of n into magnitude of z raised to minus n, right? Less than or infinity sigma, and so which means that magnitude of the whole term becomes less than or equal to magnitude of the separate individual terms. That's what this equation means, right? Now suppose this value of z can be any value, right? Is it depending on the ROC, this the value of z can always change, okay? But suppose if I put the value of z is equal to 1, or magnitude of z. Suppose if I assume that the magnitude of z is equal to 1, which means that if I'm taking my z plane, then there is a circle called as z is equal to 1 circle, right? This is called as the unity circle in which the radius is equal to 1, okay? The radius is equal to 1 in this z plane, this unity circle, okay? So if I put a magnitude of mod z is equal to, substitute the value z is equal to 1, what happens to this equation? That this equation will become magnitude of h of z is equal to, this will become less than or equal to sigma n is equal to 0 to infinity magnitude of h of n into 1, because 1 raised to minus n is 1 itself, so into 1. Here we have already seen that if you want the system to become stable, then this value should be less than infinity. In other words, the magnitude of h of z becomes less than infinity. See, so this is how we can tell whether the system is stable or not. That is, if the region of convergence has this value, that is magnitude of z is equal to 1, then I can tell that the system is stable or not. This is how we check the stability of the system. That is, the magnitude of z must have this unity circle. It should be included in the unity circle. The value of z can be anything. It can be anything, but if 1 is one of its value, if this value 1 is one of its value, then I can rest assured that system is stable or not. The system is stable. Then I can say that the system is stable. For example, suppose if I say that the ROC, okay, is between, let me give you an example, like 3 by 5 less than or less than mod z less than 2. Okay, look at this. This is an example. Okay, this means that the system is stable. How do I know the system is stable? Is because the range of z varies from 0.6 to 2. The range of z varies from 3 by 5 to 2. So when it ranges, if it is from between 3.5 and 2, then this value 1 is also in between this two range. So from that I can understand that the system is stable because 1 is between that. Suppose if I give you another ROC, let me say for example ROC is 3 less than Z less than 5. Okay, so if an ROC of a system is defined like this, that is 3 less than magnitude of Z less than 5, then this is not stable. The reason why this is not stable is because this circle is not included in this region. That is, Z can never be equal to 1, because this value 1 is not inside this region. Here the values are 3, 4, 4.5 up to 5, right? So 1 is not included inside this range. 1 is not included in this range. That's why the system is not stable. Whereas here 1 is included inside this range, right? See, for example, this is 3.5 and this is 2, right? So the range is between 3.5 and 2, which means this unity circle is also inside this range. So that's how we check whether the system is stable or not. Okay, this is how we check the stability of the system. That is, check whether the unity circle is inside this range, or the value 1 must be inside the range. If it is not inside the range, then it is not stable. If it is inside the range, then the system is stable. This is how we check whether the system is stable or not. Now next you're going to understand is how you're going to check whether the system is causal or not. How do you check whether the system is causal or not, or how you check the causality of the LTI system? Okay, we all know what is the meaning of causal system. Causal system means the system should depend only, or the output of the system should depend only on the past and the present input, right? Or in other words, the value of h of n must be equal to 0 whenever or for n is negative, right? This is called as the causality of the system. That is, h of n means h of n should have a value. There should be a value of h of n only when n is positive. Okay, and if n is negative, then h of n should become 0. Or in other words, the graph of h of n must always be and only be on the right side of the graph, or the positive values of n, right? That means h of n can be any value from n is equal to 0 to plus infinity, but it should not have a value when n is negative. That is what we call as the causal of, that's what we call as the causality. Is how we check the causal of a system. So now how will I check from the ROC of h of z, from the region of convergence of h of z, how will I check whether the system is causal or not? To find that, all you need to do is apply the same procedure, right? So here, if you understand this, h of n is equal to 0 when n is negative, right? When n is negative. So in order to look at whether the ROC of h of z, just check whether the magnitude of z is greater than the outermost value of the outermost pole of the transform function h of z, right? So for example, if I say that in an equation, like one of the equation, z minus 2 into z minus 3, okay? So here I can say from here, if the system is causal, all right? If the system is causal, then the magnitude of z is greater than 3, right? So from here I can easily understand that the system is causal. That means the z plane, if this is an z plane, then the system is said to be causal in this z plane if the ROC is the external region of the outermost pole of that z transform. So here z is equal to 2 and here z is equal to 3 are the two poles, right? Z is equal to 2 and z is equal to 3 are the two poles, right? So which is the outermost pole? Z is equal to 3 is the outermost pole, okay? Z is equal to 3 is the outermost pole. Z equal to 2 is inside the circle. Z is equal to 3 is outside the circle. And if magnitude of greater than 3 is the region, that region is the external part of that outermost pole. And if it is the external part of the outermost pole, then I can say that the system is causal. This is how we check whether the system is causal or not. Okay, so let me just review how to check whether the systems are stable and causal. That is, a system is stable, a system is stable if its ROC, if its ROC of h of z includes the unit circle magnitude of z equal to 1, right? For example, 1 by 2 less than magnitude of z less than 3, okay, or 1 by 4 less than magnitude of z less than 3 by 2, right? In all these ranges, 1 is also inside this range. The value 1 is inside this range. So that's why I can check whether the system is stable, right? Now, a system is causal if its ROC is the external region, of the outermost pole of h of z. This is how we check whether the system is causal or not, right? Or in other words, simply check if magnitude of z is greater than any value that's shown over here. In the question, when you give the question, if you see this greater sign, then rest assured it is a causal signal, okay? And if it is between, and if the value is between two range in which the one is inside this, then it is a stable. And any system that satisfies both these conditions are, then that system is both stable and causal. For example, okay, let me just give you one brief example and check whether the system is stable or not. For example, like let me give you a value. Suppose I say that that magnitude of z is greater than 0.5 or 1 by 2. Magnitude of z is greater than 1 by 2. Okay, so is this system stable? Yes. Why? Because if this is 1.5, if this is 1. Or if this is 1 by 2 or 0.5, then, and this is outside the region, and in that case the unity circle is also inside the range, right? Because magnitude of z greater than 1 by 2, then the value 1 is also inside this range, right? So this is a stable system, and this is also a causal system because the region of ROC is external to the 1 by 2 circle. See, so this system is both stable and causal in nature. Suppose if I give you another example, magnitude of z greater than 3, okay, is this a stable system? No, it's not stable system, because the unity circle is inside the or excluded from this region. Or in other words, if this is the circle, okay, if this is the circle, the radius is 3, if this is the circle, then magnitude of z greater than 3 means this is the range, okay, this is the range. So in that case, the unity circle is not included in the ROC, therefore this is not stable. It is causal, but it is not stable, right? Here this is stable and causal because one is also included inside the ROC, and also it is the external region of the outermost pole, okay? If I give you one more example, for example, if I give you a range like 3 by 4 less than magnitude of z less than 5. Okay, then this is also a stable system because the value 1 is between 0.75 and 5, so 1 is inside the range, so therefore this is a stable system. Okay, stable system. But this system is not a causal system, because a causal system means it should be greater than 5, then only it will be a causal system. So this is a stable system but not a causal system. This is a causal system but not a stable system, whereas this is a both stable and causal system. Okay, this is how we check by looking at the this is how we check by whether the LTI system is stable or not, by looking at the ROC of H of Z. Okay, so now one more thing also you can understand, that to find the frequency response of this system, to find the frequency response of the LTI system, all you need to do is simply substitute Z is equal to e raised to j omega. Simply substitute e raised to j omega. Or in other words, when h of z is replaced by h of e raised to j omega, that is the z transform function becomes a function of e raised to j omega, or simply substitute the value of z as e raised to j omega, then that function is essentially what you call as the frequency response of that system. Okay, that is also one more thing you need to remember. That's it. This is the only thing you need to understand regarding the analysis of LTI systems. Okay, so basically they will give you the questions, they will give you a difference equation, and from the difference equation you solve the value of h of z and h of n, and looking at the ROC of h of z, I can determine whether the system is stable or whether it is causal. Okay.